Hi everyone, my name is Megan, and today I'm going to be talking about optimizing gravity assist trajectories for interplanetary travel. So gravity assists, or flybys, use the gravitational pull of a celestial body to alter a spacecraft's velocity vector. These maneuvers require entering the sphere of influence of a planet or asteroid um, or any other celestial body on a hyperbolic escape trajectory. These maneuvers can be used to change the flight path of a spacecraft and can mitigate the need to carry extra delta V on board to do an actual maneuver that involves thrusting on the spacecraft to get to the same destination. So missions to reach outer planets and asteroids or comets often require multiple gravity assists and deep space maneuvers, since our current technology cannot get spacecraft so far away solely using propulsion. So an example of this you can see in the picture is ESA's Rosetta mission, which completed flybys of Earth, Mars, the asteroid Steins, and the asteroids Lutetia before arriving at its destination comet. So it would never have been able to complete that mission only on Delta V supplied by the spacecraft, because it would just have been far too great of an amount of propulsion that needed to be carried on board. So since these trajectories require multiple gravity assists using multiple planets, they are very difficult to find and optimize. There are often only very specific times that such missions can take place, since the planets need to be perfectly aligned in order to complete the transfers. So we need a really good, solid optimization method to be able to find when we can actually complete these transfers to do missions such as these. So just a little bit of background on interplanetary trajectories first. In order to get from one celestial body to another, we use a patched conics method to find the trajectories. Um, so a spacecraft must leave the first planet's sphere of influence on a hyperbolic escape trajectory and then enter an elliptical transfer orbit around the Sun. It will then enter the sphere of influence of the destination planet on a hyperbolic trajectory. And then for a flyby, the satellite stays on this hyperbolic escape trajectory and slingshots around the planet to continue on to its final destination. So in order to find all the velocities for these transfers, we use a Lambert solver. So in that Lambert solver, we're going to use the position of the departure planet at the departure date, and then the position of the arrival planet at the arrival date, and then the time of flight between those 2 points to find the velocities relative to the Sun at those 2 points, and then we'll find the escape velocity of the satellite relative to the planet it's arriving at by subtracting the velocity of the planet from the velocity found using those Lambert solvers. And there we get the escape velocities at each planet for the mission. So then, in order to understand what types of delta V and time of flights we can expect from having different departure and arrival dates, we're going to look at pork chop plots. So these are generated by forcing this simulation to look at very specific a range of departure and arrival dates, and then finding what ones use a delta V that you deem is acceptable for your mission, or a time of flight that's acceptable, or some other parameters can be looked at as well. So these can be used to narrow down the design space for optimization so that a solution can be determined more efficiently, so you can get a general idea of what you want and then hone in on the best solution using your optimization method. So since we have multiple transfers between planets, you'll need pork chop plots for each one of these transfers as you get from one planet to the next. So in order to find the optimal trajectory for interplanetary travel, we're going to need to implement a global optimization function that is chosen to minimize or maximize a certain parameter. So this parameter could be a number of things, but some of the most common ones for missions such as these would be to minimize the total mission delta V or the total mission time of flight. But choosing this parameter is really based on the objectives of the mission and the requirements of what you need to be able to do on that mission. So the problem of finding these optimal trajectories for multiple gravity assists is very difficult, just due to the nature of the problem with the planets all being in different locations at different times and the number of possibilities for getting from one destination to the next. So there are many methods of optimization that have been developed to find a solution for this. But today we are going to be looking at the ant colony optimization method. So this is based off of how ants use pheromones to help one another eventually end up finding the best path to sources of food. So they're really adept at communicating with one another to all find the best path to food sources together. So these ants have been modeled on software to be used to help find the optimal orbital path. So the algorithm generates artificial ants that find paths from the first to the last planet, and these ants then deposit pheromones at the nodes of the system based on the cost of their trip, with the nodes being the different celestial bodies that are involved in the trajectory. So you can see from the graphic kind of a general idea of like you have all the ants taking their different paths and depositing pheromones of where they were, and eventually all the ants can hone in on one single path that is the most efficient way to get to all of your destinations. So using this method requires a probability matrix that combines the amount of pheromones for traveling to the next node with the associated cost of traveling to the next node. Weights can then be placed on these two metrics to make one more important in deciding the final trajectory than the other. So the equation for this matrix can be seen here, with tau representing the pheromone to get from node I to J, and eta representing the cost to get from node I to J. And then the alpha and beta in that equation are those weights that you can place on the two metrics to emphasize one over the other in picking your final trajectory. So during its tour, each ant will visit the whole set of nodes in the system. So in order to start this process, you need a first ant to be placed at a random initial node, and then have it take the cheapest path for each node of the tour. So there will be no pheromones yet when this first ant sets out. It will set the initial level of pheromones at each node based on the final cost of its trip. And then after that, the rest of the artificial ants can begin their tours and then start leaving their pheromones. And then the iteration keeps going. In order to do this, you also need the range of possible departure dates and time of flights in order to start the process, and then and you can get these numbers from generating pork chop plots. But so once the ants have all gone through their first loop of the tour, they'll update all the pheromone levels, and then it'll just keep iterating until they converge to a solution. So each ant will only deposit the pheromone at the nodes they visited, and that amount of pheromone deposited is inversely proportional to the cost of that leg. So the lower the cost of getting from one node to the next, the more pheromone that the ant will deposit. So the pheromones will then guide the ants through the iteration and help them converge to a final optimized trajectory. That's kind of how the ant optimization method works. And then since a very common parameter to be minimized is the total mission delta V, we're going to look at the cost function that would be used for this optimization. So the cost function can be seen on the slide, and that is based off of the departure delta V, the delta V associated with each maneuver, and then the arrival delta V. And then those are all positive since we are minimizing them. And then the constraints that are commonly used with this problem are maximum allowable delta V for the mission and a maximum time of flight. So then this cost function would be used with the ant optimization method to find the trajectory that would best minimize the delta V to get from your first location to your final destination. All right, that's it. Thanks for listening.